Hey there, and welcome to this video talk on new graph decompositions and combinatorial Boolean matrix multiplication algorithms. My name is Nick Fisher, and this is joint work with Amir Aboud, Xander Kelly, Shachar Lovet, and Raghu Meka. So let me start with defining the Boolean matrix multiplication problem. In this problem, we are given two matrices, A and B, which have 0 and 1 entries, and the task is to compute their Boolean product. Now, this is defined somewhat differently than the normal matrix product. Still, every entry in the output matrix corresponds to like an inner product of a row in A and a column in B. But this time, instead of just putting the inner product there, we put a 0 there if the inner product was 0 and a 1 if it was positive. So, we instead of computing the normal matrix product, we just put zeros where all zeros were and ones where positive entries were. This is really a very fundamental problem because many algorithms throughout, many polynomial time algorithms just apply Boolean matrix multiplication as a black box in order to get speedups. Now, as it turns out, this is related to another problem called triangle detection. Here, the task is to detect in a given graph, which we can assume without loss of generality to be tripartite, whether it contains a triangle. The triangle would be like a triple of nodes in which all three edges are present. Now, both of these problems can be solved in n cubed time, and in fact, it's well known that these are subcubic equivalent in the sense that if you find a faster algorithm, faster than n cubed for one of them, you also get a faster algorithm for the other one. So let me show you the state of the art for Boolean matrix multiplication, because obviously, since this is a special case of the integer matrix multiplication problem, all the algebraic algorithms for the integer matrix multiplication problem similarly apply. So the first one, due to Strassen, this famous algorithm developed in 69, runs in time n to the 2.81, and then it spawned this long line of research on matrix multiplication algorithms after. The current state of the art is this algorithm due to Vasileska, Williams, Shu, and Zhu in time n to the 2.371552. Okay. Now, of course, many people believe, or at least find it plausible, that this approach could continue to eventually get an algorithm in time something close to n squared. But it turns out that actually in parallel to this line of algebraic algorithms, there also has been work on so-called combinatorial algorithms. I'm going to talk about that in a second in more detail, but basically just think of algorithms which do not use these algebraic techniques. So the first one runs in time n cubed by log squared n, and it's sometimes called the 4 Russians method. The idea is kind of that you can just pre-compute answers to very small subproblems. And this algorithm was later extended by Bunzel and Williams, shaving another log to the 1/4 factor, which is actually, while it seems like a weakish improvement, it's actually very, very interesting what's going on there technically. Like in their paper, they use regularity decompositions. And this is also the tool which, as you will see, is what we use to get our algorithm. This will later improve then by Chan and Yu to log cubed and log to the 4 respectively, using some smart divide and conquer ideas. Okay, now this is the state of the art before we started working on it, and in our paper we obtain an algorithm with this running time. So it's n cubed by 2 to the log n to the 1/7. So this kind of speed up, it appears often, and it's it's faster, or it's stronger than every polylog improvement. But it's not quite a polynomial improvement. So it's not quite of the form n to the 3 minus epsilon. Okay. I should also mention that it turns out that there has been, in fine-grained complexity theory, there has been a conjecture around which says, in terms of combinatorial algorithms, maybe you cannot do much better than this. So maybe n to the 3 minus epsilon is just not possible. But actually, let me talk about combinatorial algorithms for a minute. So I'm aware that this is a somewhat controversial topic, so let me be specific. Combinatorial algorithms in the context of fine-grained complexity, where we vaguely understand that an algorithm is considered combinatorial if it does not use algebraic fast matrix multiplication. Of course, this is not a formal definition, and actually, coming up with a proper formal definition here might also be actually also a very interesting question. Okay, but I understand that if you see the state of the art and algebraic algorithms seem to be much better, why do we even care about combinatorial algorithms? Well, I think there's a number of good reasons. First of all, combinatorial algorithms tend to be simpler in that you could actually hope to implement them and understand every step on like a combinatorial level. Whereas at least the state of the art for matrix multiplication becomes extremely complicated in bounding these tensor rings. Second one is practical efficiency. Again, these tensor machinery, I think even for like somewhat moderate improvement, like let's say into the 2.5, already the constants in the algorithm became galactic. So there's no hope in ever implementing a really efficient algebraic fast matrix multiplication algorithm on a chip. Whereas for combinatorial algorithms, there certainly might be some hope. But perhaps the most interesting point is generalizability. So for many generalizations of triangle detection, matrix multiplication simply does not apply, or at least not in a sense, like not in the sense that it would give a polynomial improvement. These generalizations could be in a weighted sense, in an online setting, for hypergraphs instead of graphs, or maybe in order to enumerate triangles instead of merely detecting them. And the hope is that if we could somehow manage to mimic algebraic, like the strength of algebraic algorithms with combinatorial ones, maybe we can further push them to also to also deal with one of these generalized variants. And the cool thing is that in all four of these cases, if you could give a truly subcubic algorithm for that generalized triangle detection problem, you would refute one of the major conjectures in fine-grained complexity. And it's like, some proof of concept here. In fact, what we managed to do is we do get an improved algorithm for triangle enumeration, mildly improved with respect to what was previously there, so not strong enough to refute any conjectures, but definitely showcasing that there are settings where combinatorial algorithms are better than algebraic fast matrix multiplication. Okay, so let me talk about our algorithm and the tools it relies on. So the keyword here is regularity decompositions, which, let me define it somewhat abstractly to you. Suppose you're given an arbitrary graph. The goal is to decompose this graph into pieces, abstractly speaking, that are either sparse in the sense that they have a bounded, say, edge density delta, or that they are pseudo-random in whatever appropriate notion of pseudo-randomness. So for instance, for this graph, maybe a decomposition should look like this. Okay, now this has been becoming a famous topic ever since Semiretti's regularity lemma, which is like the seminal result in math, which says it gives you a very strong pseudo-randomness guarantee. It says either every graph can be decomposed into pseudo-random pieces, which by definition, are either like actually pseudo-random or sparse. Unfortunately, though, the number of pieces in Semiretti's regularity lemma is really, really huge. So it's of the form, it's like a tower of height polynomial delta inverse. So it's like a 2 to the 2 to the 2 and so on. And this tower has height poly of delta inverse. So while this gives a lot of very nice qualitative statements, as soon as you want like a quantitative bounds, typically they become very weak with Semiretti regularity. So which led people to consider different forms of regularity lemmas, like for instance, Fries-Canaan regularity, which is a weaker form of pseudo-randomness, but it comes with the benefit that the number of pieces in the decomposition is much smaller, so only exponential in poly delta inverse. Now, what we're interested in is a notion of pseudo-randomness, which is suited at least for triangles, but which comes with even fewer pieces. And it turns out that we exactly develop a regularity decomposition for this kind, so which is pseudo-random for triangles, but the number of pieces is now, instead of being exponential, it's this expression, which is just quasi-polynomial in delta inverse. Okay, now why is this interesting? How would we be able to gain from such a regularity decomposition? Let me show you. The idea is actually very simple. And as I mentioned before, we're also not the first ones to apply regularity decompositions to the triangle detection problem. So also that's what Banzhal and Williams did. So they used a different regularity decomposition, but from like this high-level point of view, also their algorithm is kind of the same. So the algorithm is, you start from this graph, as I said before, let's suppose it's tripartite, you compute a regularity decomposition. So this decomposition consists of some pieces like this, right? So you have some subset of nodes and some subset of edges, which are either pseudorandom or sparse. Now, if this piece was pseudorandom, and under some appropriate notion of pseudorandomness, which should behave like it should work with respect to the triangles, then we would expect a pseudorandom part to contain many triangles. simply because in a truly random graph, you would expect many triangles. A graph where, say, every edge is uniformly sampled and independently from all other edges with some probability. So in the algorithm, if there is a pseudo-random piece, then we simply return yes without any other consideration. The third step is, well, there are a lot of pieces in the graph which are sparse, delta sparse specifically, so we should expect a speed up of delta with respect to the Naive algorithm if we only solve all the sparse pieces. Okay, so the running time would be something like this. The running time we spend on the sparse pieces is delta times n cubed. But of course, we also first have to compute the regularity decomposition, which then takes time n squared times the number of pieces roughly. And plugging in our new bound on the number of pieces, which is like quasi-polynomially, you get this running time trade-off, which is optimized by setting to n cubed by 2 to the log n to the epsilon, setting delta to be 1 over 2 to the log n to the epsilon. Here epsilon is some absolute constant depending on what exactly is this quasi-normal expression. For us, it turns out to be 1 over 7. Okay, so this is like the recipe of how to turn this regularity decomposition into a triangle detection algorithm. And in fact, for the rest of the talk, I will just focus on this regularity decomposition, which is really like the innovative part of our paper. And to put this into some context, turns out that actually this is the third paper in a line of research, which was started last year by Zander and Ragu's result, like an actual breakthrough result in additive combinatorics, where they proved almost tight bounds on the size of 3 arithmetic regression-free sets. Then in a second paper, and together with Shachar, they extended these analytic techniques from like the arithmetic setting to graphs. And this defines a very nice notion of pseudo-randomness, which is what we want to rely on in this paper. Okay, so in this paper, then we use this notion of pseudo-randomness, and we develop an appropriate regularity lemma for this. And as I said before, we get all these algorithmic applications. So in order to be like somewhat formal, let me define what is this notion of pseudo-randomness that I keep talking about. So let's start with bipartite graphs, where the node sets are denoted x and y, and the edges in the middle are denoted by a. Let me also denote the density of A, the delta of A as the number of edges divided by n squared. So here's a good notion of pseudo-randomness, d-spreadness. A graph is d-spread if there is no induced subgraph on many nodes, specifically 2 to the minus d times n many nodes, which is significantly denser than the original graph. So say it's denser than like 1.01 times the original density. This is clearly a property which would be true for a pseudo-random graph, for a truly random graph, so that's a good sanity check. And it also turns out to have very nice mixing properties. Unfortunately, this property is not really well suited for us because we are interested in an algorithmic setting. And d-spreadness is something which is somewhat hard to handle with. So finding obstructions against d-spreadness, which would be like a large, dense subgraph, finding this is actually somewhat hard. And even just testing whether a graph is d-spread is quite non-trivial. So instead, what we will rely on is another notion of pseudo-randomness called d-grid regularity. This is something which showed up, interestingly, as like an auxiliary notion of pseudo-randomness somewhere in the proof of Zander, Shachar, and Ragu. And this is the definition. So it's defined as, we say that a graph is d-grid regular if the number of k2d subgraphs, so the number of 2 times d bicliques in this subgraph, in this graph, is at most, this 1.01 times this expression, which is just the number of k2d subgraphs or in a random graph. So the expected number of bicliques in a random graph. So grid regularity says you don't have significantly more bicliques as subgraphs than a truly random graph would have. Okay, now this is much nicer from an algorithmic point of view because, even testing whether the graph is grid regular is somewhat easy by just sampling a bunch of bicliques, like sampling a bunch of 2 nodes left, d nodes on the right, and testing whether they form a biclique, for instance. Okay, now still, why are these useful measures of pseudo-randomness? Well, it turns out for a bipartite graph, they're not necessarily what we would guess is pseudo-random. In fact, they don't really give you any guarantee on bipartite graphs. But what these guarantees do provide is a very nice mixing property. So let's consider a tripartite graph. Now the nodes through x, y, and z, and the edges between x and y are a, the edges between y and z are b. And suppose that the edges are d-grid regular, respectively, like both the edge sets a and b. Then, as they prove, all pairs x and z, now you take a node from x, you take a node from z, have approximately the same number of two paths, namely exactly the number you would expect in this graph, like density of A times density of B times n. Okay, now that's not exactly true, but in fact, this is true for all but a 2 to the minus d fraction of these pairs. So for almost all pairs, you have exactly as many, or approximately as many two paths as you would expect. Now, I should mention this theorem also does have another technical condition, which actually is also very important for the decomposition, well, in our paper. But, for simplicity, I'm just going to ignore it in this talk. Okay, why is this now a useful notion of pseudorandomness with respect to triangles? That's what we're shooting for, after all, right? So suppose you add a third edge set to the graph. Let me denote it by C. And also suppose that this edge that is dense, so has density strictly bigger than 2 to the minus d. Well, then the graph must contain a triangle, right? Because there must be a pair x and z, which is on the one hand connected by an edge in C, and on the other hand has approximately that many two paths, so in particular at least one two path. So you find a triangle. Okay, so that's a good notion of pseudorandomness, which is kind of saying that if you get a graph where A and B are regular and C is dense, then it contains a triangle. Now, what we need is a regularity decomposition, which decomposes an arbitrary graph into pieces which are either pseudorandom in the previous sense or sparse. Good. So let me start with the bipartite graph again. And just show you the theorem which we get. Unfortunately, I won't really have time to talk about the proof here. So the theorem says that, as I said before, you can decompose this graph into pieces, and pieces the form, x, y, y, I, a, I. These are a subset of nodes and a subset of the edges between xi and yi, respectively. Now we want the following four properties. We want that the edges are perfectly partitioned into the edges in the respective, across all pieces. Like every edge appears exactly once. Sure. The second one is every piece is either sparse, which formally means that the density of the piece is at most 2 to the minus d, or it's pseudorandom, which specifically means that the edges AI, they're d-grid regular. Okay, nice. The third property is somewhat technical, which it's kind of saying that this is an almost decomposition. So formally, this says that the volume of every piece, which is like the product of the node sizes, if you sum them up across all pieces, this basically becomes just x times y, which would be like the original volume, up to some small overhead, the form poly d, which is small enough such that you can actually ignore it in the end. And finally, we want to bound on the number of pieces, which we managed to prove was 2 to the poly d. Now, if you think about it, right, with respect to the sparsity threshold we specify here, which was 2 to the minus d, this is actually a quasi-polynomial bound. Okay, so that's kind of what we want, except, of course, that now we're decomposing bipartite graphs, and, this notion of pseudorandomness is not really expressive for bipartite graphs. We really need that when you really need to consider tripartite graph, where the mixing applies. So what we really want is to consider a tripartite graph and get a similar decomposition into pieces like this, still like subsets of nodes in x, y, and z, subset of edges of A and B, such that the following stronger properties are true. So instead of decomposing the edges now, we want to decompose the two paths. So every two path in the original graph appears in exactly one piece. Moreover, each piece is either sparse, which now means that at least one of the edge parts AI or BI is sparse, or it is pseudorandom, which means that both the edges in AI and BI are d-grid regular. We still want the almost decomposition property, which is now defined on like the volume of like a cube. And we still get the same bound, like the same bound number of pieces of form 2 to the poly d, maybe a slightly worse dependence in the poly d. Okay, great. So that's kind of exactly what we were hoping for, because now on every such piece, you can apply the previous slide, which says if the respective edges in C between these parts are dense, then there must be a triangle, and otherwise, well, these edges are sparse. So you really get a decomposition into pieces where each piece is sparse or pseudorandom. Okay. Final thought, of course, well, we are interested in an algorithm in the end, so we also better be able to compute this theorem, which can be done in time n squared times 2 to the poly d. Somewhat more easy by a randomized algorithm, but in fact, we spend some more work and get it in deterministic time n squared times 2 to the poly d. Okay. Now, as I said, I won't have time to actually cover the proof of this, so I'll leave you with some open questions, though. So open question 1 is quantitative improvements. So can we improve the constant 7 in our exponents? Or, it seems reasonable that at least we should be able to go down to something like 2 to the square root log n. But perhaps there's even a tweak of this which allows you to achieve polynomial improvements, which would be amazing, of course. The second and perhaps most interesting one, as I said before, is can we satisfy the hopes on combinatorial algorithms and actually make this work for a generalized setting like weights, the online setting, hypergraphs? All of these would be really interesting. And as a reminder, for these settings, matrix multiplication typically does not apply, or does not apply in a very satisfactory sense. So it would be really amazing to make these combinatorial techniques work. And third question, which is maybe a little bit more mathy, is all of what we're doing here seems very related to triangle removal lemmas. Unfortunately, we couldn't really see make our regularity decomposition work in order to prove an improved triangle removal lemma. But still, it would be very interesting to see whether at least some of these ideas carry over, and perhaps you might even be able to prove the same quasi-polynomial improvement for triangle removal. Okay, that's it. Thanks for listening.